Okay, my screen is visible, right? You're able to see the presentation, right? Can someone just
Yes,
confirm if
we
yeah,
can.
okay.
Yeah,
Yeah,
we can see
okay.
the slides as well.
Yeah, thank you so much. Yeah, okay. So today, what I have planned for today will be an absolute beginner-friendly session on agents. So I'll walk you through like what AI agents are, the current scenario as in what frameworks are available, what is the real-world use cases where you can use the AI agents. We'll also look at the building blocks, how agents are actually executing, and we'll also look at some of the career opportunities. I have added it as a kind of end slides because um, of course basics are important. Before you go into agents, it is always good to learn the basics of ML. You need to understand LLMs, and then you have to switch to AI agents. But today I'm not focusing on all that. Instead, we'll directly start with what agents are and how we can use agents in real world. So that's the agenda for today. So basically, an agent, you can consider it as a software system. What does it do? It basically interacts with the environment. Uh, Anything, be it a user or even there are physical agents where it interacts with the environment, takes the input from the environment, and based on the instruction, it acts on the instruction. And it can also think using the memory that is available to the agent, and it can adapt to whatever feedback the environment and the user provides the agents with. So it does all these things. It perceives the environment, it reasons about what it is supposed to do based on the instruction, and it takes action, and then it learns and adapts based on feedback. So how is it doing it? It basically uses LLM as the brain. So large language model sits as a brain, and whatever decision the agent is supposed to take, it is taken by the LLM. And the LLM is also provided with something called tools. The agents are provided with tools, and it can execute those tools based on the reasoning. And once it shares the output to the user can basically give feedback about the output, and it takes the feedback, it iterates on the feedback, and it gives better output. So this is what exactly an AI agent does. And you can see the basic definition of agent in Artificial Intelligence, a Modern Approach book. And this is the definition. And it is applicable to physical agents as well as software agents. So agent can be anything. It can be a physical agent, it can be in a simulation, it can be a software system. So it can be anything. If we look at traditional agents, the physical agents that I was talking about, a simple example would be a reflex agent. A reflex agent is something that just has if else condition. It will work only on follow, it will work on rules. It will follow the fixed rules that we provided to the agent. Assume that we have a thermostat in a room and it has a sensor, it can sense the temperature of the room. What it will do, if the temperature goes down, it will automatically turn on the heater. So this is a very simple instruction, and this is also an agent. So the simplest form of agent is a reflex agent. Example is thermostat in a room, and there is no learning here, there is no memory here. All it does is read the instruction and it follows the instruction. That's it. Next, we what we have is goal based agent. Example, we all have smartphones, and we do have iPhones, and there is Siri. In Google you have again you can use okay Google, and you have Alexa. So there are a lot of agents like this which are goal based, in the sense it will understand what you talk, it will look up for relevant information that you are asking for, it follows our commands, and it can give you the answer. And it has very limited autonomy, in the sense it can still search for answer in certain apps. It cannot access things that you have not given permission to. So ideally it has limited autonomy, but it will follow your instruction, and based on that it will share information. And it is like interactive. You keep asking questions, it will give answers. So this is based on a certain goal. So that's why this is called goal based agent. And then comes the autonomous agent. Autonomous agent is something which can first understand what you are providing as instruction. It can break the entire task into subtasks, which can be easily done by the agent, and it can write code, it can search for information, it can do everything that a human can do, and it will iterate till it finds the right answer. So all this can be set by the, of course, there is a human involved, but it will try to find the right answer till the criteria is met, till the instruction is met. So here we give it some autonomy. You tell the agent that you can search the web, you can access the files, you can read, edit, you can do anything that you want, but I need the final output. So that is what autonomous agents are. And these are the agents that we are using and we are talking about today. So example is there is this open source agent called Devin, which is like a software engineer. So you give the agent a task to build an app, it can read the instruction and it will automatically build the entire app for you, like how a software engineer would sit and research and read and do coding, do testing, deploy the app. All that can be done by this agent. So this is one example of autonomous agent. So these are the different types of agents, but again, right from physical agents to software agents. And when we talk about agents, it has four distinct blocks. So you have to, whenever someone talks about agent, you have to think of these four items. One is the brain, which I spoke about earlier. So brain is the decision making block, which is your LLM. You can use any open source or paid or proprietary LLMs to do the reasoning. So the agent becomes powerful based on what LLMs you use. If you have an LLM that is very strong with reasoning, then your agent will also be a very good agent. It can think and try to find the right solution to the problem that you have. So that the LLM decides what to do. How it is supposed to do, that is done through tools. So this is the action layer. So here we give permission to the agent to access APIs, to execute code, to search web. It can read and write from database, it can access your files, provided you give permission for all this. It will not do anything beyond your control, like uh, based on complete instructions that you give and complete permissions that you give. The agent will be able to execute all these tools. So this is the action layer where the agent actually interacts with the world. Then you have a memory block, because the agent has to remember what it has done and it has to use that information in the subsequent conversation, right? So this is the state management layer. So here we have different mechanisms. You have very like limited memory, like short term memory, where a model has ability to handle, let's say, 1024 tokens only. So you can give only a paragraph of instruction and data, you cannot give more than that. But what if you want to feed the agent a 100-page document and you want to ask the model, ask the agent to do a certain task? Then you need to increase the memory capacity by using something called vector database. You can have RAG, retrieval augmented generation, to process the knowledge between the conversation. So this way you are providing the agent the ability to remember things. So that is the memory block. Then the agent needs to plan using certain strategies. So I give a task, but it needs to understand and figure out, okay, this is how I'm going to do it. So it needs to plan. So what it will do, it will break the task into multiple tasks, small tasks. Then it can reason, execute tools, use the memory, and then give the answer. So all these four blocks or layers work hand in hand. And here there are multiple ways of planning, like you have chain of thought, you have react, you have plan and execute. There are multiple strategies that it can follow. So the core building blocks of any AI agent is these four. So you whenever someone talks about AI agents, you need to think about all these four items. When we also talk about agents, traditionally we have used chatbots in many systems, and we also have built ML systems, right? Traditional machine learning systems. So people might get confused between agents, chatbots, and ML pipelines. So here I just wanted to give a brief of what is the difference. So in traditional chatbot, there is no autonomy. Like it will wait for your instruction. Only when you ask question, it will answer. And it cannot access anything beyond what it already knows. Like you have given, let's say, FAQ document for a specific website. If it is there, you can create a chatbot on top of it. So it knows only that FAQ document and nothing else. So it cannot access the web or it cannot do anything beyond that. It knows only the current conversation, and user needs to keep asking the same question multiple times. It cannot remember because it does not have any memory. The simplest form of interaction is what it happens in the chatbot. Whereas in the ML pipeline or ML workflow, we build a model. So it knows that, okay, I need to first do data processing, then build the model, then the model will be used for inference. So there is an order, and we have defined that sequence. And it can access only those methods. Let's say data pre-processing is a method, and it will use that method. There might be some post-processing method to filter out the results once the model gives the output. So all these are already defined, and it has access to only those methods. Methods and tools are kind of interchangeable, so it has a very fixed tool sequence. And you need to call those functions explicitly in a ML workflow. So after step one, you have to call step two. After step two, you have to call step three. So that is also defined in your ML pipeline. If there is a failure, what does it do? We would have already defined some fallback mechanism, and it will use that, and it will keep retrying. Let's say it needs to reach a specific website. We'll say that, okay, try for 3 times. And if it fails, just say you are not able to reach the website. So these things are already written and fixed logic, and that is what will happen in the ML workflow. Example for this is RAG pipeline. So RAG is the retrieval augmented generation, where you have a vector database where you embed all the documents. A user can come and query about a specific document, and it will first retrieve the relevant answers. Then we use an LLM. We feed the retrieved relevant documents, and the LLM will use only this context to answer the user. All this is predefined sequence, and it will follow the same steps. So that is what ML pipeline is. Again, here it will have limited access to only that document. It cannot search beyond that documentation. Whereas in agent, what will happen is you give it a set of documents, but you also allow the agent to access web. You also allow the agent to have memory. You tell the agent to think and self-correct it. So all these instructions are already given. So what it will do, it will only decide the next step. You give the problem statement, and it will say, okay, this is the problem statement, and I will do these 3 steps. And it will automatically pick the relevant tool needed for those steps. Then you already have provided some long-term memory or short-term context, and it will use that memory, and it will try to get the answer. And if the answer is not satisfactory, it will only self-correct. So all this is done on its own. But even here, uh, a user like us will define all these things, but the execution and everything will happen on its own. In other things, that's not the case. It will do only predefined steps. Example for an agent is, say, Devin is an open source, accentuator to a software engineer. You have Claude Code, you have AutoGPT, you have a lot of agents. So this is the difference between traditional chatbots, ML pipelines, and agents. When we talk about agent, this is the loop that it follows. Like I was talking about steps, right? What does it do? What does the agent do? Whenever a user gives a task, what it will do is it will observe. Observe is the first step. It will read the context and gather more information about the given task. So this context, it can be in forms of document, it can go and all this is provided in the instruction itself. So if we will provide something called context, and then we will share a lot of information to the agent. So it will read the context and gather whatever additional information is needed. Once that is done, it will think. Which will think? The LLM will think. Based on the context, the LLM will try to reason, okay, this is what I'm supposed to do. Okay, for this step to happen, I will do steps A, B, and C. And then it will plan. That is the thinking step. After that, it should act on the steps that it has already defined. So it will start calling tools based on the step. Let's say you want to solve a mathematical problem. You will need certain formulas. So in the LLM reasoning part, it identified the formulas. In the act part, it will actually execute those formulas with the numbers that you have provided. I'm just telling a simple example. Then once it executes, then it will check whether it has executed the step correctly or not. Is the goal met? So this is what the user wanted to do. I have executed. This is my final answer. Is the final answer satisfactory to the initial goal? If not, it will keep repeating this loop of observe, think, act, and evaluate till it feels that okay, this is the final answer I have got and I'm satisfied. Then that will be given to the user. And even the number of tries it has to try can be fixed by the user. Otherwise, it keep going in loops, right? So even that can be provided as an instruction. So this is the set of steps that an agent takes when it is executing for a specific problem. The same thing here, it is in the form of code. So you create a memory. Here it's just a simple list, but a memory can be a database, it can be a rack system. What it will do is LLM will think first. It will break the steps problem into steps. So this is the planning phase. Then it gathers information about the current context. Then it will take action. Then it will think and then take action, and then it will basically evaluate. While evaluating also, it keeps looping. So if the plan is whatever plan it starts with is satisfied, then it will come out of the loop. Otherwise, the loop will happen. It is not an infinite loop. We can specify the number of times it has to try and all that. So this is how in pseudocode, this is how it works. Now we'll have a look at the different types of agents. Okay, so there are depending on what it is trying to solve and how it is solving, you can start from a very simple agent, which is a reflex agent, the thermostat example we saw earlier. So it just acts on provided condition. That's it, nothing more. There is no memory, there is no learning, nothing. It will just use the current rules and it will execute the solution for the problem. So this is the simplest agent. Then we have the model based agents. Model based agents are basically nothing but you build model for a specific problem, an ML problem. Here, for example, self-driving car. A self-driving car has to navigate the road. So you would have built a model using lot of roads in different lightings, different angles, with vehicles in front, without vehicles, different road conditions and all that. And that model will basically in real time capture the road. It will see what is the object in the front. Should I increase the speed? Should I apply brake? So all this is done based on the models learning. So that is why this is a model based agent. So any ML system that you have can be, it is a model based agent. Then we have a goal based agent. Here, all the gaming examples, like people talk about a lot of games, right? You have chess, you have computers playing chess, you have like there is this backgammon game, lot of games, anything that a computer plays. So there is a goal, like you need to win. It can be a zero sum game, it can be a multiplayer game. So all this is goal based. Ultimately, you have to win the game. So you use the knowledge of the environment, the simulation, and you take action. The agent takes action. So that is what a goal-based agent will do. Then we have utility-based agent. Here, there is a utility function, and the objective of the agent is to maximize that utility. For example, in recommendation system, we have different types of users using Amazon, right? But for every user, you get different kind of recommendation. How is it happening? Because every user preference is different. The user characteristics is different. The purchase pattern is different. So you take into account all this information and you model it as a problem. Again, it's a mathematical function where you are trying to increase the utility. So whomever is the user, based on them, the recommendations will change. So recommendation system is an example of a utility based agent. Then we have the learning based agent, which is the AI agents that we are talking about. Anything that uses LLM to make decision, uses tools to execute and improves based on feedback, because there is some learning that is happening over time. It adapts over time based on the user feedback. So this is the learning based agent. So you have this AlphaGo machine, AlphaGo system, which is built. I think long ago there was a paper on that, and you have lot of modern LLM agents. Anything that has to do with, say, customer support. Yeah, you can have agents for like even writing documentation. Any task that you can think of as tedious, we do have a lot of agents for them. So these are the type of AI agents. So the simplest one is on the left and the more complex one is on the right. So AI agents can be built for any kind of use cases where you think you can reduce the repetitive work. There is a lot of redundant work that we do on a day-to-day basis. You can use agents to replace your redundant work, not the creative work, but then you can take help. For example, even coding is, I understand, like there is a great shift after the advent of AI agents, right? There is a great shift now. Like people don't generally code these days much. People use Claude Code or Copilot. They give instructions, the agent codes. But ideally, it's a good thing to code yourself and learn the basics. But there are scenarios where you have to churn out multiple things, and if you are an experienced person, using agent can be a very good addition to your everyday work. But if you are a beginner, I would highly suggest use agents cautiously, but learn what is happening behind the scenes, even if you use it for research or use it for coding or anything. So there are agents for coding, example, Claude Code, GitHub Copilot, Cursor, etc. So what it does is, based on the information you provide, it can write code, debug the code, execute the code and deploy. But only challenge is you should be in a position to debug the code also. Not all the answers or all the code that is provided by agents are 100% accurate. So you should always verify whether the output is correct, it is factual or not. So that is very important. You have research agents like Perplexity, OpenAI, Gemini, where you can go and ask a question and ask them to provide the relevant links. It can even tell you step by step. It can give you, like you want to make a documentation, it can do anything, but it can do deep research also. For that purpose also, you can use research agents. So slowly people are moving away from Google uh, Chrome to research agents, so which is also a good thing. Then we have in the industry side, when you think about, we do have customer support agents. There are products that have been built. So these are all AI agents, Decagon, Sierra. These are some of the agents that can to look at customer tickets, resolve, it can answer questions, it can do everything. A customer support agent is supposed to do, a human is supposed to do. It can be replaced by agents. Then we have AI agents for doing data analysis. You can provide it with a lot of data. It can ingest the data, run analysis, and it can produce visualizations and all that. So what used to be a data visualization, data analysis used to be a specific stream of ML, but now it can be done by agents directly. So data analysts, there is a role called data analyst. Now they can use this to make their jobs easier, actually. And there is DevOps SRE agents like Shoreline, PagerDuty, where it can check if the cloud environment is always up. If something is down, it can check the root cause and provide a fix. So that is also one of the useful agents that people use in the industry. Then comes the personal assistants like Zapier, Rabbit, or One. These are some of the devices that you have. Some are software, some are actual devices where you can program the device to, like you can tell the device to do what you want to do. Say, I want to book a flight, please book a flight. It will access your information, it will book a flight for you. It can fill forms, it can manage workflows. So this can be your complete personal assistant. So now we looked at all like the basics of what is a agent, what are the core steps, how it will think, how it will plan, and all that. Now I'm getting into the key concepts one by one. So we talked about tool usage, right? That the LLM thinks, and then the agent actually executes certain methods, and those methods are basically called as tools, and function calling. They call it tool and function calling. Okay. So what is function calling? Basically, LLM will apart from generating text, that's the main use case that we all know for LLM, but it can also create API requests which can be used for calling external functions. Okay, so that is basically function calling. So it will you will be able to call a third party API using an LLM. Example is, let's say I want to know what is the weather in Tokyo right now. What will the LLM do? First, it will think I need to have a weather tool because the user is asking about weather. Then it first creates a tool called to weather and weather information, weather API. Then it sees that it is the city name is Tokyo. So it passes that as an argument, and the agent will execute this weather API. Once this is done, the weather API returns the temperature. Then the LLM actually makes it as a proper readable sentence to the user, and it shares the information. This is the example. So analogy is like, imagine LLM as a chef in the kitchen. The chef knows the recipe. He knows what to do, but how he will do? Let's say first he wants to make a roti. Then what he will do is he will first get all the ingredients. So getting ingredients is one function call. He will get the mixer, put the flour, mix it with water, all that, and then he bakes it, or he makes roti and he puts it in the pan and gets it. So he knows what tool to call at the right time. So that's exactly what an LLM does. So you can compare an LLM like a chef in a kitchen. Once the results are back, he will taste the food. If it is good, he'll serve it to the customer. If not, again he may remake. So that's exactly what will happen in tool use also. So you call a tool, you get the answer. The answer is not satisfactory. You again change certain things, parameters, and you call again and you may get the right answer. So this is exactly how the agent will call the tool, like function calling happens. Then we also know that the agent has memory, right? So memory can be short term. Short term is you just provide one document to the LLM call, and it will use that information alone, it will answer. So it's like, right now you have this problem and you want to solve it. You know only that information and you will solve it. That's enough. That's the short term memory. Example, you are solving a problem in math. Let's say you want to calculate LCM of two numbers. You just need to know the current thing and just current numbers, and you calculate the LCM. That's it. In long term memory, you need to remember stuff. For the current question, past information might also be very, very essential. In that case, what you do, you have something called vector database, where you store the conversation as embeddings in the vector database. So whenever someone asks a specific question, we first go and search the vector database, pull all the relevant information, and use that as a context to the LLM, and it will answer the current question. So this is like expanding the brain of the memory of LLM. Then you have the retrieval augmented generation. This is also same as the long-term memory, but only thing is, here we get the relevant document, then we feed it to the LLM. It will understand the relevant documents, then it will try to answer the question. So just like you have access to 10 books and you want to answer a specific question, you go through all the 10 books, but all 10 books will not have relevant answer to the question. Maybe two books have a similar topic, then you pick only the two book, understand the entire context, and you answer the question. So that's exactly what RAG does. So in short-term memory, the context window is very less. So you can have maximum 1 million tokens. Whereas in long-term memory, you can have a vector database of terabytes of data. In RAG also same. It's dynamic knowledge. More than lots of, I don't need lots of information. I need quality relevant information. So the knowledge is dynamic here. So that's why you can use any of these type when you are building an agent, depending on your use case. Then once you have memory, you know you have chosen the LLM, you have chosen the right memory. Then you need to figure out how to plan things, how the agent should execute stuff, right? It has access to tools and all that, but now how to execute, in what way it should work. So these are the planning strategy that the agent can take. There are multiple. The most common one is called the react pattern: reason and then act. So what it will do is it will first think. Okay, I need to find the population of France. So the question is, tell me the population of France. Then it will take action. So it will use the tool to find population of France. Then it will get some answer. Then it will again think, do I actually have the answer? Yes, I have the answer. I can respond. Then it provides the answer. So it will think and then act. It will react is reason and then act. Reasoning is basically thinking. So that's why this framework is called React. So this will show us how the LLM is thinking. If something is wrong, we can always observe it from the steps, right? And we can provide a better instruction. So that's why this framework is what is widely used in the industry. Again, here I have given some examples also, which you can go through. I will share the slide after the session. So here, a detective is trying to solve a case. So as and when he gets the clue, it is leading to new scenario, right? And finally it may lead to the killer. So this is how the reasoning framework works, the react pattern works. Each clue leads to the next action, and each action will result in an answer, and the model will think if it has the answer. If so, it will give it to the user. So that's what happens in the react pattern. In chain of thought, what happens is, again, it will try to do it step by step, and it will show it also to the user. So here, let's say we need to multiply two numbers. Directly, if it provides answer, we will not know what exactly happened in between, like what steps did the LLM take. Instead, it will try to break the problem into steps like this. Just like how we used to solve maths problem on exam, right? Like directly, if you provide answer, people will not accept it because they want to know the thought process. So you will ideally, with the formula, you start substituting the values, then you solve it block by block, and then finally you arrive at the answer. So that's exactly what chain of thought does. This is a very simple technique, but very powerful in terms of knowing how the model is thinking. So this is the thinking out loud paradigm, if you can call it. So here you can see examples like where to use it. Whenever you need the system to be accurate, but not necessarily fast, because this takes a lot of time. If for everything, it will think and it will show it to you. So it takes time, but it is very, very crucial in terms of getting accurate results. So that's where you will use chain of thought. The next strategy is plan and execute. Here, first the model, whatever LLM that you have chosen, will break the problem into multiple steps, and each step will be executed by a smaller agent. Instead of one big model executing everything, here it will delegate the work to multiple agents, and it will wait for output from all of the steps. And finally, it will collate everything and it will provide the answer. Just like in an industry, like when you're running a project, there is a project manager. Project manager himself will not sit and do the coding, right? What he will do, he will uh, put the tasks in a sheet. He will assign the tasks to different people. He'll see if the different software engineers are doing their work, get the results, collate it, and then present it to the client. So that's exactly what happens in plan and execute. There are many frameworks where this is used in LangGraph, Baby AGI, and there are many production systems where we use this strategy. Then what we have is the reflection strategy. So an agent can execute, it can get answer, but it will also fail. So what should it do when it fails? It needs to reflect. Okay, this is where I went wrong. So what should I do different so that I get a better answer? So that's exactly what this strategy does. So it tries to, let's say, the question is to sort a list using Python. There are two methods in Python that you can use to sort a list. One is sort, another is sorted. So sort and sorted are two different things, but does the same sorting, but it does it in different way. Sort uses in-place sorting. So the same list, whatever you provide, that itself will be changed. Whereas sorted provides a copy of sorted list. So What if the user wanted a copy and not alter the existing list? So the model first tries to use the sort method and then it fails because this is not a sorted list. Then because it does it in place, the answer, the reflection is it modified the original list, but the user wanted a copy. So what it does is, in attempt to, it tries to use the other method and it passes the actual test case that the user has provided. So this is the reflection loop, and it will try to solve the task, evaluate if it meets the test cases. If not, it will reflect why it failed, and then it will retry till it gets the right answer. So this is in similar to how games are done. Teams play. Let's say there is a football match. A team has lost the match. So what they'll do is they'll go back and review what exactly went wrong, like which player contributed to more mistakes, or what the player could have done to solve, like win the game. So they analyze and then in the next game they rectify it. So that's the reflection strategy. Then we have the tree of thoughts. Tree of thought is same as chain of thoughts, but the same thing is applied in multiple ways, as in parallelly you evaluate multiple approaches for a problem. Say for a problem you have three approaches and each approach has multiple ways to solve. Then you see, you score these methods and find the best one and you provide it as an answer. So this is just like in normal tree methodology. In one branch, in one way, maybe one leaf will be the best answer. Other leaves are not the best answers. Something like greedy method kind of thing. You go through all the path, find the best one, and you share it with the user. So that is what tree of thought will do. If an agent follows tree of thoughts, this is what will happen. So it will generate multiple candidate reasoning paths, and it will evaluate using a certain heuristic that is set by the user. Whatever is the good ones, promising ones, that will be used, and highest scoring solution will be used to the shared to the user. Example is chess. Every move results in different kind of progression of the game, right? So what will a chess player do? He will think, okay, if I use rook, what will happen? If I use a pawn, what will happen? They will think internally, and they know the progression of the game, right? If they make that move, and finally they choose for the current set of pieces in the current places, what is the best move that I make. So that's exactly what tree of thoughts does. And this can be used for like very creative tasks or puzzles or code generation and everything, because you can solve the same problem multiple ways, but you need uh, a method that is easier and complexity wise less complex and all that. So you can use this strategy for such problems. So till now we have seen like a single how a single agent will work, but in reality we do have we what we have is multi-agent systems. Like uh, LLM will actually spawn multiple agents and each agent will do its own task. So this is literally like running a software engineering team. So so I have a team of people working with me, right? So each person does different jobs. So my job is to delegate the work to them. So I'll tell them, do this, do that. Okay, this is the project. This is how it should be done. If this is the task, this is how it should be done. So you have a project manager, you have a designer, you have a front end developer, back end developer, you have a QA person. Same thing, you can spawn agents for all these tasks, all the work that you want to do. For example, there is an orchestrator that will be me. Assume that it's me. My job is to just assign tasks. I will not do any work. In the sense, I will not do hands-on, but I will first identify what should be done, how it should be done. All that will be decided by me, and I assign this task. I coordinate with the team, and I get the output, and I collate it. Right? That's the work of an orchestrator agent. Then you have a researcher agent, which will go and research the web, find relevant information, summarizes the information. So that is a researcher agent. Then you have a coder agent. After the research is done, you input that to the coder, and what the coder agent will do, it will basically code based on the provided instruction. It will code, fix bugs, run tests, do everything, deploy, all that will be done. Then you have a reviewer. You can even review a code written by an agent. So this reviewer, ideally in real world, I will be reviewing, like I'll be doing orchestrator work and reviewer work. I will also review the output. If there is any quality issues, I'll share them input on how to improve the quality and all that. So that's what a reviewer does, reviewer agent does. Then we have a writer agent. Then in writer, what it will do, based on whatever is the system, it will create a technical report. It can format the output. It can provide visualizations. It can do everything. So you can simulate a software engineering team using a multi-agent system. So not just, this is one example, but you can do anything that you can think of, any task that you can think of. Each of your subtasks can be an agent. You can do a dedicated agent for that, and the agent will do the work and it will bring it to you. And as a human, you have to be in the loop and you can analyze the output. You can figure out if everything is right. Then you can go ahead with collating the information and share. So this is what a multi-agent system does. And some of the frameworks which you can use to develop this multi-agent systems are Crew AI. There is AutoGen from Microsoft. There is LangGraph, OpenAI Swarm. Anthropic has SDK where you can code and uh, do this multi-agent systems. So here are some of the examples, like whatever I spoke about yesterday. So these are some of the open source ecosystems. You have paid ecosystems also. So for individual development work, most of the things are free, even the paid ones. But when you have to increase your limit or you have to use it for multiple purpose, you have to get a paid version. So you have LangChain and LangGraph, where you can do all that they have said. You can have memory, you can choose the LLM, you can use a lot of tools, and then you can orchestrate. So it is available in Python and JavaScript. Then you have Crew AI. Even here, it's very easy to define and orchestrate the agents. Then you have AutoGen, where you can build multi-agent conversation systems. The agents themselves talk to each other and they solve the problem. Then you have SDKs. SDKs are for people like me who needs control. Like in the sense, there are no code platforms also, but if you are a software engineer and you need to have control of all the agents, you can actually write the code using the APIs and you can build the agent. So that way, you know exactly what is happening behind the scenes. So you have OpenAI SDK and Anthropic SDK. Then you have Hugging Face small agents. This is also a very lightweight agent framework where you can code and you can build agents, and this is based on transformer models. So these are some of the frameworks and tools available. You can feel free to Google them and check them out. So this is a very, very simple example of, again, the weather tool that I was talking about earlier using OpenAI SDK. So all you have to do is install the relevant Python frameworks for Python, and then you can directly call them. You can call the agent. You have a runner, you have a function tool. Function tool is nothing but you define a method. Method is normal Python method, let's say adding two numbers or getting weather or reading a data from a file. All these are simple methods. All you have to do is add a decorator called function tool, and this will be used as a tool by the LLM while it is calling the tool. You can add hundreds of methods like this. Whatever your agent is supposed to have access to, you can add this decorator on top of that method, and that will be used by the LLM. Then you define the agent simply by providing the name of the agent, what it is supposed to do. A weather agent can go and check the weather. So you can provide instruction like, okay, you help users check the weather and what tools it needs to access. So get weather tool is what it has to access. This is a very simple one. You can make it as complex as you want. You can create an agent, you can provide a very elaborate instruction, and you can provide hundreds of tools to access. So it will decide which tool to access based on the instruction. Okay. And the result will be you run it, like you execute this agent. You provide the user query. User query is what's the weather in Paris. So automatically it will know it is a weather agent and it needs to use this get weather function, and it will take the city from here, which is Paris, and it will find the answer. It will give you the answer. That's it. This is a very simple example, but you imagine you can do this for any kind of complex task. So all you have to do is define the relevant tools using this function tool decorator. Then you can create an agent by giving it a name, set of instructions, and all the available tools. And then you can run it. Then you get the answer. That's it. This is the flow of building a agent using again this SDK, but there are no code platforms also where you don't even have to write code. You can just drag and drop things and connect things to build your agent. Now that we have seen the basics of how to, what's an agent, how to build and all that, I also want to talk about the limitations, because just because it is doing a lot of stuff a human can do, it is not magical. It is not magical. It always has a lot of limitations, which an LLM has. Because large language models, though it can do a lot of things, it comes with a list of issues as well, right? So the primary one that I want to talk about is hallucinations. I was talking about fact checking, right? Whatever an LLM gives as answer. So since the agent is relying on LLM as brain, you need to fact check all the answers provided by the agent. You cannot with 100% confidence say, okay, this is right, I will use it as is. No, you should not use it. You should always have fact checking mechanism. You should be available in the loop. You have to verify everything and then only pass it to the end user. Okay. So this is very, very important. You have to address hallucinations. Then cost and latency is a very important thing. When you are using it for a very small project like college project or a toy project, it's easy, it's fine. You can wait for a long time. You can afford the, maybe sometimes it's free, sometimes you need to pay it. But imagine building a big production system. People can't wait for a long time. Your response has to be there in milliseconds, and then latency should not be there at all. So you have to make sure you are using the right strategies like caching your prompt, using right model, right infrastructure for reducing the cost and latency. Otherwise, you will pay hundreds of dollars of money every month if you don't do that. Then reliability and looping. Like I said, we do loop the agent till it gets an answer. But what if it keeps going on in loop forever? That should not happen. You should always have an observability stack where you track what an agent is doing, how many times it is trying, do you have exact fallback mechanisms if something is failing. All this should be in place. So you have to take care of reliability and looping. And security risk is major concern in deploying these systems in production, because it should not have access to things that are private or that are not supposed to have. So there might be attacks on the system by prompt injection, and an adversarial user can just change the prompt and send an API call. All this will happen in real time. So you should always put some guardrails. You should have some input validation. You should have some sanity check and all that. Otherwise, your system is at risk. You should never ever put a production system without these guardrails and other like sandboxing in place. Then people forget about evaluation. Like, okay, when you are talking about productionizing systems, we will do everything, but how will you tell a system is good or bad without quantifying it? How can I tell that an agent is a good agent or a bad agent? So always you have to have a set of data which is evaluated by humans, and the agent, whenever it gives output, a human has to sit and benchmark that result. Otherwise, you can never say something is good or bad. Just by looking at it or just by feel, you cannot say. You need measure. That's why it's always good to have a golden data set and benchmark the results. So that's what evaluation should actually do, and we should do it for every project that we work on. Then we have context window limits for the agent, right? Because we are using LLM. LLM comes with its own limitation of context. Some models can handle 1024 tokens. Some models can handle, let's say, 10,000 tokens. Some can handle only 784 tokens. So there is limit. So you need to figure out a way to expand the context window by using methodologies that I was talking about, like adding memory. You can have better chunking strategies. You can summarize the input and give so that the context is captured as a summary. So all this has to be taken care of if you are building production systems. So till now, I was talking about the tech side of things. Now I wanted to talk about opportunity also, because I know a lot of you will be looking for jobs after you graduate. So maybe there are several roles. So here I'm talking about the latest kind of roles that people talk about after LLMs and prompt engineering and all that. But traditionally, any ML role that you know of earlier, now it has all transformed. Okay, so now everyone uses on work, everyone uses cloud code, copilot and everything. So we definitely use some AI tool in our day-to-day work. So our roles have also transformed. So earlier what used to take let's say 1 week to build, now I can build that in a day. But what I am bringing to the table is the expertise, or over time, whatever basics that I have learned, the experiences I have gained, I am using that to steer my AI tool. So that's exactly what you should also do. Like, you should learn the basics, you should understand what goes behind the scenes, and then use that information to use the AI tool efficiently. Just simply asking the AI to do everything is not good. And you cannot sustain with that kind of skill set, right? You need to improve your core skills and then use that to leverage the AI tool. So that's the thing that you have to do. And here I'm talking about general roles that are available right now, and these are the approximate salary range in the global market. It may vary from country to country, but this is on a global level. So you have a traditional AI ML engineer role where you will build software systems also with AI in it. So you will build AI systems, you will build agentic systems, you will build rack systems. So you will do end to end, not just API calling. You may even build models or use existing models, tweak the model, fine tune the model, and you build the entire system. So that is what an AI ML engineer will do. A prompt engineer is more on the uh, like, they will not build the system, but they will tell the system what to do. So you can you will come up with proper instructions, you will create system prompts, user prompts, design reliable reasoning mechanisms and all that. But at least from my experience, I have not specifically seen a standalone prompt engineer role. It will be like combined. AI ML engineer and prompt engineer is kind of combined, but there are companies which hire for only prompt engineer. And you have agentic developer roles. So AI agent developer role, where you build only agentic systems. You don't care about the traditional systems. Instead, you work completely on the agentic system. So you take care of like whatever multi-agent systems we saw earlier. You will build that system, deploy that system, monitor that system, evaluate that system. So this specific role is completely on the agentic AI end. And you have the architect role. So these are the beginner roles, or like maybe intermediate roles. And the final one is the solution architect, where you know everything, you know the basics, you know the enterprise requirement, and you build enterprise ready system. Not everyone can do this. This comes after years of experience, but you start with all this, you learn, and then finally you will reach the AI solution architect level, where you will build end-to-end systems, integrate with existing systems. You will do everything basically. So that's the AI solution architect role. For all this, the key skills that you need to learn, first is Python. You have to be a very good Python programmer. You can still use AI agents to code and get the code, but underlying architecture decisions, like how efficiently you are using the code, how efficiently you are using the memory, how what data structures are you using, those are still very important in building production systems. If you do not know that, even if you use AI tools to build, and you can still pass it, but then you will not be able to survive in the industry for long. So uh, learn the basics of Python, learn the basics of ML also, because without ML, you cannot, without the core concepts, you will not be able to learn the subsequent things. Then you need to learn the LLM APIs like OpenAI APIs or any other frameworks API. You need to learn them. Then you need to know how to prompt a model. Again, this is trial and error initially, but over time you will learn the pattern. Like, okay, this is how I should ask a model to answer, and it will give you the right answer. Then you need to understand how vector databases are created, what kind of algorithm it uses to index the data, what algorithm it uses to retrieve the data, all that. Again, I'm talking about the core of vector database, not just calling the API. So you need to learn that. Then system design is very, very important. Whether you like it or not, learning software engineering skills is very, very important. Without that, you cannot architect systems. Just by putting together three, four function calls, you cannot uh, build a high quality system, right? So you need to know system design. Then finally, you need to understand how to evaluate the system and test the system. There is no generic way of testing it. For every system, for every domain, for every problem, you have to design different set of evaluation and test suite. Otherwise, your system, you cannot quantify whether a system is good or bad. Then I have provided some resources also here. So some roadmap to how you can go ahead and learn. Okay. So you can learn basics of all these LLMs, understand the prompts, tokens, tool usage and everything. Then you can start building agents, simple agents with all the frameworks that I was talking about by adding memory and all that. This is by month one, you will be able to build simple agents. Then you can go for multi-agent project where you build together, put together a set of agents together and then build a system like, okay, code reviewing or like blog writing and all that. Like you can do everything using this multi-agent system. You can pick a problem that you think is interesting and you can try to do this. Then finally, you can add evaluation, observability, deploying. All this is very advanced skill. You will also need to learn cloud skills and all that. And finally, you can even contribute back to these frameworks so that, it will tell you that you have learned what is needed and you are able to contribute back to the frameworks. So this is again a very basic roadmap, but you can tailor it to however you want to, and some resources I have provided. So yeah, I think that brings me to the end of the presentation. But I just wanted to reiterate on one thing. Though the session is on agents, learning the core of AI/ML is very, very essential. Only then you will be able to understand why a specific agent works that way. So key takeaways from this session should be like, get your basics right, learn about agents, learn about the basic building blocks of agents, start building small agents, then go for multi agent systems. Then once you do all that, learn the framework, try doing this multiple times, you will master that skill. And because right now the market is very dynamic and you have lot of career opportunity, so if you take enough time to master these skills, I'm sure you'll be able to uh, you know get very good opportunities in the market. So that's all I have for today. I think I'm done with the presentation. And if you have any questions or anything, you can basically share it now, or you can reach out to my LinkedIn also. I'll be active in LinkedIn, and I can provide answers there. Yeah, I think that's all from my end. Yeah, I'm done with the session.
Abhi, can you hear me?
Yeah, I can hear you only now.
This is Samantha.
Yeah, hi, ma'am, hi.
So first of all, thank you for giving a talk in AI agent. Hope our students get some understanding the industry trends and the way they need to focus. So I have a question regarding the LLM and the vector database. So how they are playing in AI agent, like so, what
Yeah,
is the connection? Let's say if we wanted to develop an agent for data analysis based on our student management system. So, we already have a database, right? So, let's
yeah.
say we want to analyze the data. So, that agent should work like based on the student data, it should give something. So, then where the vector database is and where the LLM is in that scenario.
Okay. So you already have an existing database present, which has all the information.
Yeah.
That is like your traditional structured database. It's like tables. You have information about the student or everything about the student. Vector database is a different system where you will store only the embeddings. When I say embeddings, you have models. There is something called embedding models. What it will do is it will take in whatever text you give, it will try to convert it into vector embeddings and it will store it in that database. That database is needed when you have like lot of textual information, because text is quite huge, right? The context is high. For a structured table, you don't need much. You don't need to convert it to embedding. You can directly give the. You can have the existing database, and LLM is a separate block. LLM, what it will do is you give access to the existing database to the LLM. LLM can go and read the database, and a user comes and queries this LLM. Okay, I want to know certain information about a student. Can you give me? What it will do is it will go and pull the information from the table. It will try to modify it based on the user query and it will share the information. So this is the agent I'm talking about. Here the memory is already in the form of existing database, and LLM will be your brain, and the user can query it directly. But if suppose you also have additional textual information about a student or some other documents, let's say joining formality, you ask them to fill a lot of documents and you have it as doc files or something, then that can be embedded and stored in a vector database. Now the LLM will have access to the vector database also, and you want to ask if the user, the student has filled in those forms, analyze those forms and tell me if they have missed to fill anything. Now the LLM, what it will do is it will try to, agent will actually use this LLM. This LLM will go and call the vector database. For a specific student, it will pull all the relevant documents. It will understand if everything is filled. If not, it will try to tell the user that, hey, you know what? These are the checklist for joining, but this particular student did not fill, let's say, document B. So this is how the system is connected. So you can have multiple databases, multiple um, systems, and the agent, you have to tell the agent that you have access to all these systems by function calling. I was talking about that function calling, right? So you provide the permission to the agent. It will automatically decide which database to access, and then it will use that information and it will share it with the user. So this is how you will orchestrate the system. So you don't basically need to create a new database also, since you already have one. You can still use the existing system, and it will answer the user query. So this is how you can connect the systems.
Okay, thank you. It makes sense. Any other questions? No. Okay. So I hand over to our team. Okay.
Yeah.
Good afternoon, everyone. On behalf of the IEEE Women and Engineering Affinity Group of the University of Jaffna, I would like to express our sincere gratitude to everyone who made today's Tech Talk a great success. A special thank you to our speaker, Abhinaya Mahendran, CTO of Nunneri Labs, Coimbatore, for delivering such an insightful and engaging session on Agents 101. Your clear explanation and real-world perspectives truly helped us understand the importance and future potential of intelligent AI agents. We would also like to thank the Department of Computer Science, University of Jaffna, for providing the venue and continuous support. Our heartfelt thanks go to the IEEE student branch and WIE committee members of their dedication and teamwork in organizing this event. Finally, thank you all the participants for your active involvement and enthusiasm. We hope today's session inspire you to explore more in the field of artificial intelligence. Thank you all and have a wonderful day. Before we conclude, we would like to express our heartfelt thanks to our speaker, Abhinaya Mahendran. Although today's session was conducted virtually, as a token of our appreciation for sharing her valuable time and expertise with us, we will be sending the token of appreciation to her. Once again, thank you very much for insightful and inspiring session.
Thank you so much. Thanks, everyone. Thank you, ma'am, Samantha, ma'am, for inviting me. I really enjoyed sharing my time and sharing my expertise. Thank you so much, everyone.